Welcome to This Explainer. Today we're diving straight into a massive, looming challenge in the tech world. We're going to unpack exactly how the semiconductor industry is racing to completely reinvent computer engineering, basically to save the AI revolution from its own massive energy demands. It's this incredible story of physics, engineering, and just sheer innovation.
To really grasp the sheer scale of the incoming crisis, we have to look at where AI is actually heading next. Researchers are estimating that emerging multi-agentic AI systems, and by that I mean systems that don't just chat with you, but actually take specific tasks and execute them completely autonomously, will require a staggering 150 times the compute power of our current large language models. The shift from simply training these models to running continuous, highly complex inferencing workloads is creating a demand for power that's honestly almost unimaginable. And this staggering requirement is exactly what led Patrick Van den Emel, the CEO of IMEC, to ask a pretty terrifying question. Can we scale AI without exceeding infrastructure and planetary limits? It makes it crystal clear that our current playbook for scaling AI hardware just isn't sustainable anymore. We absolutely can't keep building bigger data centers using the exact same old architecture, because if we do, we're quite literally going to run out of power. So here is our roadmap for today's explainer. We'll start with the AI scaling crisis, move into physical AI at the edge, explore the full-stack solution, dive down into thinking in 3 dimensions, and wrap up with the massive ecosystem effort required to pull this off. All right, part 1, the AI scaling crisis and the end of linear scaling. Here's the crucial point to understand. Right now, AI power consumption increases almost entirely linearly with compute. Today's playbook is pretty straightforward, right? You scale compute to its absolute maximum die size, run a ton of GPUs in parallel inside a rack, and connect those racks into a giant factory. But because it scales linearly, processing 10 times the algorithms requires 10 times the hardware and power. Because of this, modern data centers are now literally measured in gigawatts rather than megawatts. This linear path is exactly what Patrick Van den Emel was warning us about. It just doesn't truly scale. Which brings us to part 2. Physical AI at the edge, where AI actually enters the real world. This perfectly illustrates the divide between where we are today and where we're going. You see, AI is leaving the server rack. It's moving into humanoid robots, self-driving cars, and smart hospitals. Cloud computing is incredibly forgiving. If your AI image generator takes a few extra seconds or messes up, you just retry the prompt. No big deal. But physical AI at the edge, it demands zero latency, life or death, microsecond responses. The workloads are highly heterogeneous, which means they require adaptive architectures, mixing standard CPUs with specialized programmable hardware like FPGAs. And most importantly, failure is catastrophic. There are absolutely no second tries in a hospital setting. Salil Raji over at AMD paints this incredibly high-stakes scenario to really ground the engineering challenge we're facing. Imagine you're at work, and you get a text that your parent has fallen at home. Do you call emergency services and wait 15 minutes? Or do you deploy the humanoid robot that's already in the house? The real question isn't whether the robot can physically walk over to them. It's whether the edge AI inside that robot is fast, deterministic, and fault-tolerant enough to act correctly and safely in a delicate, very human crisis. So, to make these edge devices intelligent and safe enough to handle those scenarios without literally burning up their batteries, the technology has to radically shift. Manufacturers like TSMC are stepping up here by migrating edge components to their most advanced nodes. They're actually driving operating voltages down to 0.4 volts. Why? Well, because that tiny voltage drop achieves up to a massive 70% reduction in switching power. This is exactly how you make edge AI viable without needing a portable power plant in your pocket.
Moving on to part 3, the full-stack solution, where we take a multiplicative approach.
The reality is that we need a jaw-dropping 10x gain in compute efficiency over the next decade, and we can't just make transistors smaller anymore to get there. Those days are mostly behind us. Instead, we have to use what's called System Technology Co-Optimization, or STCO. Basically, this means innovating across this entire stack. If we improve the algorithms, the architecture, the packaging, and the communication fabrics all at the exact same time, the efficiency gains aren't just added together, they multiply. This multiplicative approach is quite literally the only mathematical way to outpace the insane power demands of AI. And the industry giants are fully embracing this. As Samsung's CTO points out, they're breaking down those old traditional product silos. For example, instead of keeping logic strictly on the GPU and memory strictly on a separate chip, Engineers are now shifting some core logic directly onto the high-bandwidth memory base die. By co-optimizing across these domains, they dramatically improve speed and power efficiency, bringing the processing right to where the data lives. Let's zoom way in for part 4, thinking in 3 dimensions, down at the micro scale.
Take a look at this roadmap from IMAC. They're essentially the premier research hub for the global semiconductor world. This anchors all these abstract ideas into a very clear path forward up to 2040. We are moving entirely past nanometers and into the angstrom era. We're talking measurements smaller than a single atom, which means we need entirely new physical structures to make this work.
One of the biggest leaps on that roadmap, slated for around 2033, is the CFET. When you shrink logic down to these angstrom nodes, you basically just run out of horizontal real estate on the silicon. So CFETs force engineers to fundamentally think and build in 3D. They're actually vertically stacking the NFET and PFET transistors, essentially the positive and negative building blocks of the chip, right on top of each other. It's a radical reimagining of logic devices, even pushing power delivery to the backside of the wafer just to free up a little more space.
And that 3D thinking extends all the way up to the packaging level. Right now, we generally put chips side by side on massive flat bases called interposers. But IMEC is proposing something called volumetric 3D. Imagine shifting from a sprawling, flat 2D suburb straight into a dense, vertical skyscraper. They literally want to bend an active interposer around high-bandwidth memory modules, plugging them into vertical slots like old-school DIMM cards, complete with built-in microchannel cooling plumbing, and then capping that whole cube with the main processor.
Now, the core financial and manufacturing problem that volumetric 3D solves is absolutely massive. Today's massive 2D substrates are incredibly difficult to manufacture flawlessly. If one tiny piece of that huge passive substrate fails, you might have to throw away the whole entire thing, along with thousands of dollars worth of perfectly good memory chips attached to it. Volumetric 3D shrinks the footprint, makes the memory totally modular, and drastically reduces those catastrophic yield loss issues. It's a total game changer for manufacturing economics.
Finally, part 5, an ecosystem effort, essentially collaborating to survive.
Because, let's be real, these challenges are so insanely immense that the old days of a single company doing everything entirely in-house, those days are over. Collaborative R&D ecosystems are absolutely essential now. For instance, UMC is working on the silicon photonics to move data using light. Brewer Science develops the advanced materials needed for these crazy new 3D architectures. And Synopsys builds the software tools to design and validate chips that don't even exist yet. Sharing risk and accelerating time to market is quite literally the only way the industry survives this transition.
As we completely overhaul global infrastructure, rewrite the algorithms, and literally stack atoms in 3 dimensions to deliver this intelligence era, I want to leave you with one pivotal question. Think back to that falling parent scenario. Would you trust a physical AI with your loved ones today? Probably not. So the real question is, what will it take for the semiconductor industry's new Moore's Law to change your answer? Thanks for joining me on this explainer today. I really hope this helped you map out exactly how the future of hardware is being built.